During my presentation, I will, let's say like first I will introduce a little bit more about us, about our company. And then I will talk about PolarDry technology to let you know why it can be an alternative technology instead of freeze drying. And after that, we will give some examples, some experiments, some experimental data to show you the applications that we get. And at the end, we will give a very short summary. So first, talking about fluid air. You may not be very familiar with fluid air, our name. However, you may heard something from spraying systems. Spraying system is our mother company, and it is very well known in the world for spraying nozzles. So just to give you kind of some image, we sometimes, depends, we also can eat hamburger, the breast. So you see like the brown layer on the top of the hamburger bread, it is very polished, it is very smooth, and it may be sprayed by, let's say like it is maybe coated by spray nozzle from spraying systems. And another example is that from last year, we always talk about disinfection because of the COVID. And with spraying system, we also have some divisions, which is responsible for the spraying system for the disinfection of the hand. So we have other divisions, and fluid air is one of the divisions of spraying systems. Fluid air is founded almost 40 years ago, and we joined spraying system since 2009. In this picture, you can see the building. It is a very nice building, and it is also our headquarters in Naperville in the US. We have 8 different laboratories worldwide, and we are responsible for fluid bed, high shear granulation, size reduction, and process automation. Since 2016, we launched into the market a new technology, which is electrostatic spray dryer PolarDry, and it is also the topic of today. So in this map, you can see our lab centers in the world. We have the lab centers. I hope that you get my the mouse on the screen. Not really, I guess. Okay, so we have the lab centers in the North of America, and we also have the lab centers in Europe, in Asia, and in Australia. So because most of us are based in Europe, so I would like to introduce the lab in Nantes, in France. It is a lab, let's say like specialized for microencapsulation. Here we have the laboratory models. And also, if you are interested in some trials with us, we can also introduce you to the lab in Naperville in Illinois, where we have the very big model, the industrial model. However, today we don't talk so much about the lab. We want to talk about the technology. And just to get you, let's say like to talk a little bit more about this technology, let's get some introduction first. In this slide, you can see that we have 2 very common types of medicines. On the left-hand side, it is the capsules, and on the right-hand side, it is the tablets. With the capsules, the 2-piece hard shell capsules, we know that we can put everything inside. It can, I mean, like in terms of physical form, it can be paste, it can be liquid and powders, so on. And with these capsules, everything, the excipients are not very complicated. The recipe is also very simple. However, the encapsulation is very time consuming. On the right hand side, we have tablets. With tablets, we must definitely need to work with powders. And the recipe will be very complicated because we need to make it available for tablet press and compression. However, this technology is very, let's say like it is much more time efficient in comparison with encapsulation. That's why we are still talk a lot on the powders in tablets. To get the powders, we usually use drying technology. As you already know, freeze drying is a very, let's say like common technology using for pharmaceuticals. And I guess that I don't need to talk more about freeze drying because we have all experts here talking about it. So the biggest problem of freeze drying is time and energy consuming. So think about the previous slide when I talked that we want to have the powders, we want to use the tablets because we want to have time saving. So this one is really something that we need to concern. On the right hand side, we see the conventional spray drying, which is a very, let's say, like nice technology because it is well known since a long time. And the process is continuous and also commercial available. However, the biggest problem is about the temperature. We have to apply the high temperature, which may damage or influence the activity of the API in pharmaceuticals. And remember that with both technology like that, we still need to care about the particle morphologies and properties because we want to have tablets. So because of it, we were thinking of something in between, a bridge in between freeze drying and conventional spray drying, which can combine both advantages of freeze drying and conventional spray drying. And this technology is something that I will explain today, PolarDry electrostatic spray drying. So before talking so much about technology, let's warm up a little bit with some videos that I'm going to show you now. In this video, the first one, I will show you the experiment on the hydration. Just to spoil you a little bit before the videos, let's say like the videos is very fast, that's why I have to talk a little bit in advance. In this video, we will put some powders in a beaker of water, and the water is keep under stirring. And what we want to know is that if when we put the powders there, if the powders will be very well hydrated or not. If the powders are well hydrated, it means that the color of the water will turn to be turbid or cloudy. And if it is not very well hydrated, it can be just float on the surface. And in this way, I mean, we still have the very clear water. So let's see what we have here. Now is the video that we already put some powders from the traditional or conventional spray dry, and we'll see that the water still stay very still and clear. So with this one, we put a little bit of powders from PolarDry, the technology, and you see that after a very short time, just a couple of seconds, you see that the waters turn to be very turbid. And it means, or it demonstrates that our powders have a very good hydration. So with this powder, we save it in our store for 1 year. And after that, we came back and we decided to test the flowability that you will see in the next video. In this video, we have the powders in the glass clock, and we check if the powders will be flow very easily or not. On the left-hand side is the powders from conventional spray drying, and you see that it's stuck. But then with PolarDry powders on the right-hand side, you see that the particles flow very, let's say, very well. And remember that this powder, we save it already 1 year, or let's say like it is aged 1 year. So you see that we have a very good hydration, we have the good flowability with the PolarDry technology. So let's see what is PolarDry. In this slide, you can see that it's a very nice picture of our machine. And I promise you that the machine is as nice as this picture. So there is very less Photoshop in this picture. In this one, you can see that here it is, I guess that you don't have the mouse. So yeah.
Yes, the mouse is working, thank you.
The mouse is working, thank you. Yeah. So here you can see that we have on the top, it is the spray drying chamber. And below it, we have the separation plenum, which is, let's say, like, which serves for the purpose of separation of the exhausted gas from the products. And the products will go down and will be, let's say, like, will be collected on the bottom. So let's see how it works. It is the schematic diagram of this machine, where we have the drying gas introduced from the top, and also the fluid, the feedstock, is also introduced from the top. So here we have the drying chamber. On the fluid or the feedstock will be atomized and will be dried together with the drying gas. And at the end or at the bottom of the drying chamber here, we have already the dry particles. So we have the mix of dry particle together with the exhausted gas, and we need to filter the exhausted gas from the particles from the dry products. And here we have the separation plenum. In the separation plenum, we have a filter, and the exhausted gas will go through the filter. And in the small model, the exhausted gas will be discharged. In the bigger model, we want to recirculate the drying gas, and we will have to take the exhausted gas through the dehumidification unit, and then we will heat it up and come back to the machine. The products will fall down and will be collected on the bottom. So it looks very nice. However, you haven't noticed the difference here. Where we have the magic is here on the top of the machine, where we have the electrostatic nozzle. The electrostatic nozzle is actually a bifluid nozzle where we introduce the feedstock together with the atomizing gas, as you can see here in the middle of the figure. So the feedstock will be charged with the high voltage. And then after that, it will be mixed with the atomizing gas. And then we will have the, let's say like we will spray, and we have the atomization of the droplets, and the droplets will be dried. So the good effect here happens thanks to the electrostatic effect that I will explain you in the next slide. Let's talk first about the drying curves. On the left-hand side, you can see the drying curve of conventional spray drying, where we have two periods. The first period is the constant rate period, where the drying temperature of the droplets doesn't change. In this period, what we have is that we use the heat from the drying gas as the latent heat, just to evaporate the water on the surface of the droplets. At the end of this period, we have the shell formation, where the shell is already dried, but we still have a lot of water or humid inside the wet particles. You can think of it as when you bake a cake and then you have something from outside which can be already dried, but inside there's still a lot of moisture. Then we still have to continue drying. And then from this critical point, we have the shell formation, and all the moisture from inside of the wet particles will have to be transported to the outside of the particles, and it will be continuously dried. And at the end, we have the dry particles, but then the product temperatures also increase a lot. And at this moment, is this period, we have the, let's say like the heat from the drying gas is used as the sensible heat. So on the right hand side, you can see that we have the drying curve of PolarDry electrostatic technology. So with PolarDry, what we have is that based on the polarity of the components, the water will be driven to the outside of the droplets. It means that something like, just to make a kind of imagination, we have like the droplets where the outer layer of the droplets is the solvent or the water, and the inside is the active that we need to dry. So it means that during the drying time, we just need to evaporate the water from the surface, and we don't need to apply the heat for the water or the moisture from the inside. So we can, let's say like, we can avoid the shell formation. And the biggest benefit is that we will see that the outlet temperature is much lower than in comparison with conventional spray drying. So in fact, what we did is that when we have the experiment, the lowest inlet temperature can be 60 degrees Celsius, and the outlet temperature can be 35 degrees Celsius. And because all the water is driven to the surface, so we still can maintain a very low moisture content of the powder, and also the very low water activity, as you see from this slide. So in terms of microencapsulation, we have some other effect. So on the left-hand side, you can see that it is the wet particle where we have carrier, which is the gray color, the solvent as blue, and the active as yellow. So after drying with conventional spray drying, what we have is that we will have the matrix of all the active and the carrier distributed together. So the active can be both inside and outside of the capsule. So what about with electrostatic spray drying PolarDry? What we have is that, as I talked in the previous slide, we have the stratification of the components. And the most polarity, the component which have the highest polarity will be driven out. And in most cases, it will be the solvent or the water. And the non-active, the active, which is usually the non-polar component, will stay inside. And how can we think about it? Like we have a droplet, when the core is the active, the middle layer will be the carrier and the outer layer will be the solvent. And at the end, what we will see is that we have the dry particles where we have all the actives very well protected by the carrier, as you see. Or in other words, we have the very high encapsulation efficiency. The encapsulation efficiency, of course, depends on the process parameters, but it can be up to 95 to 98%. So to work with it, we have different models for electrostatic spray drying. And you can see from the left to the right, we have the models from the, let's say like the laboratory scales to the pilot scale and also to the industrial scales. What we call here is not, let's say like it's not specifically like that because it depends on the application. This model can be already the industrial scale. So with different models, what we can say is that we offer the different, let's say like models that you can suit your purpose for the experiment or for the trials. So let's say like some data that we have. As I said before, we want to focus on the application of pharmaceuticals, but pharmaceuticals is not only our only purpose of our system. We also can work with food or with nutraceuticals and even also other biological technology. So let's see. At first, I would like to, let's say, like to give an example of working with vitamin C. In this experiment, we use two different technologies to dry vitamin C. On the left-hand side is the conventional spray drying, and on the right-hand side is PolarDry. In this experiment, vitamin C is formulated together with modified starch and maltodextrin, and we dry with two technology as I mentioned. And you can see on the left-hand side, it is the SEM image of the powders from conventional spray drying, where you can see that we have very small, let's say like the powders, the primary size of the powders are very small. And the yellow bar that you can see here is 50 micrometers. On the right-hand side is the SEM of the powders achieved by PolarDry. And as you can see that we have a very big powders, or let's say like the powder size is much bigger than the other one. So let's see from the number. In this graph on the left-hand side, you can see it is the cumulative distribution of the particle size. And you can see that with PolarDry, it is denoted by the blue color, and with conventional spray drying, it is denoted by the gray color. With the 90%, from here we can see that 90% of the powders from conventional spray drying has the size, let's say like below 100 micrometer. And with PolarDry, we can see that the D90 that we have here is about, I think that there's something a little bit wrong with my number here, but yeah, with the D90 that we have here is about like 600 or 700 micrometers. So it's just to say that with PolarDry technology, we have the agglomeration of the powders. And with this one, it is very good in terms of tablets, because let's look at the table here. In the table, we can see that the first line here, the first row, it is the target of the tablets. When we want to have the fine particle below 20%, and the oversize of the particle, which is larger than 850 micrometer of 0%. And the intermediate particles or size should be from 125 to 425 micrometers. And you can see the comparison of spray drying or conventional spray drying powders and PolarDry, where we see that with conventional spray drying, we have 94% of the powder below 75 micrometers. And it means that we need to put a lot of binding glue for the tablet. And with PolarDry, we can see that we have, let's say, like the percentage of fines together with intermediates are much more suitable for tableting. Based on this experiment, we decide to do further experiment with vitamin D. And this experiment will work together with rocket. With this experiment, we formulate vitamin D. First, we solubilize the vitamin D in corn oil, and after that we mix it or we formulate it with maltodextrin together with modified starch. And the powders is dried, and you can see on the left hand side it is the some properties that we achieve here of the powder mix. In this one, I want to point out that with the CAR index, when we have two different lots of vitamin D, we both have the CAR index of around 10%. So it means that we have a very good flowability of the powders. And then after that, we use it to make the direct compression with a single punch machine. And the data can be are shown on the right hand side. With this one, you can see that all of the hardness of the tablet, let's say like between around 15 Newton. And we know that with this hardness, it is the tablet is good for the oral tablets. Then the disintegration time, all of the experiment, we have the disintegration time of below 1 minute. And it also means that the tablet is suitable for soluble or also for dissolvable tablets. The friability, all of them have the friability below 1%. And it means that the PolarDry powders is suitable for direct compression of tablets. In this slide, I will talk about another application. Before we talk about the bigger agglomeration, because we want to have the tablets. But here, I want to talk about the inhaled drugs, where we are interested in the, let's say, like the size of 3 to 5 micrometers. With this work, we collaborate with Spera from Switzerland. And yeah, luckily we also have him today here. So with this work, basically we just want to make the comparison of PolarDry of the powder of the lactose from micronization and PolarDry. On the left hand side, you see that it is the commercial lactose from microsphere. This is experiment. Let's say like it's not experiment, it's the commercial, it's already commercial available. And the micronized lactose have this, let's say like the morphology, like as you see here, that we have like different morphology, different shapes. And with PolarDry, what we have is something like all of them are spherical. So let's see how it is with the cumulative distribution function on the right hand side in the graph. Here we show 3 different powders. The blue one is a PolarDry. The green one is the micronized commercial. It is actually the Lactosphere as you see on the left hand side. And then the gray one is the generic commercial. So we see that the generic commercial has a very big particle size, and we can see that the D90 is about 100 micrometer. So with PolarDry, what we have is, let's talk about D50. It's better to compare here in this slide. So the D50 of the generic commercial is about, I would say, 50 micrometers, and with both PolarDry and together with micronized commercials that we have, it is about 3 micrometers. So with this experiment, we just want to show the first evidence of electrostatic spray drying applied for inhalation. Of course, in the future, we don't want to have the bimodal distribution like that, but it really serves for the first evidence. And it means that PolarDry can be also served for this application. So PolarDry, as we talked before, we also want to use the lower temperature, which can be applied for thermosensitive products. In this experiment, first we make the comparison to see the influence of the temperature. So with the experiment, we dry Lactoferrin. You know, Lactoferrin is the gold milk. I would say it is very expensive, of course, because of the bioavailability and also other properties. So with this experiment, we dry Lactoferrin and we test the active Lactoferrin by ELISA assay. And in this graph, you can see that we lose the activity of Lactoferrin by using conventional spray drying at 150 degrees Celsius. With PolarDry, what we have is that we use 90 degrees Celsius inlet and 35 degrees outlet. And what we have is that we preserve perfectly 100% of the active Lactoferrin. And also when we make the comparison between freeze drying and PolarDry, as you see in the picture in the middle. So here you can see the difference of the colors together with the morphology of the powders, and we can see that with freeze drying, of course, we have the broken shape of not the powders, I would call it the cakes or the sheet. And with PolarDry, we have kind of spherical particles, which is very good. So from this slide, what we can say is that by using PolarDry, that we use the low temperature, we can preserve the high bioavailability of the thermosensitive products. And also, not by using PolarDry, we can avoid the problem of the morphology of the powders, which we usually have to face with freeze drying. In the next slide, I would like to talk a little bit about microorganisms because we are also interested in, let's say, like biological products. And here we have the experiment with probiotics. And you know that the probiotics are thermal and oxidative sensitive, and it may lose the inactivation after a few months. So in this experiment, we work with the plantarum together with maltodextrin and skim milk, and we make the microencapsulation of this probiotic. We make the comparisons of the viability between freeze drying, which is green, and with PolarDry, which is blue. So you can see that with the viability after drying that we can preserve is very high and very comparable with freeze drying, which is 10 to power 10 CFU per gram. And after, I would say like after 5 months, we still can preserve a very high viability, and it of course also decrease, but from the 6th month. So I would say like here, what we have is that we use PolarDry with a low temperature, and with the low temperature, we can preserve the good viability. And there another effect that I didn't talk before. I always use the word drying gas, not drying air, because actually in our machine, we use nitrogen as the drying gas. We have 2 reasons to do it. The first one is that we don't want, because in our system, we charge with the high voltage. So the first reason is about safety. And the second reason is that when we use the nitrogen, we can control very good the humidity of the drying gas, and also we can preserve the oxidation of the products. So one of the last slides, yeah. In this application, I just want to show a very nice images of the future application for insoluble drugs that we usually have to use the, let's say like we encapsulate the insoluble. I'm sorry, let me formulate my sentence again. So we have to formulate the insoluble drugs with some oil, and then we need to encapsulate it by microencapsulation to preserve the products, the active. And from here, in this experiment, we make the challenge to work with the essential oil, which is mint oil. And the mint oil here is encapsulated with modified starch. So on the right-hand side, you see that is the products from freeze drying that we already know the problem of the morphology. And then from the two SEM images on the left, we can see that is from conventional spray drying and PolarDry. And you can follow the yellow arrows here that you can see the very small dots on the surface, which is the oil stained on the surface. And we saw more dots on the surface or more oil on the surface in conventional spray dry powders than in PolarDry, that we can see a very, very well encapsulation efficiency because of the less surface oil. So with this one, of course, it doesn't say any number, but it's just the way that I want to conclude my presentation with the part of applications. Then to summarize, I would say that in our system, we apply the electrostatic effect, and thanks to it, we can work with the low operating temperature, and we can have the high encapsulation efficiency. The all-in-one system is something very nice, but I didn't have much time to talk about it. So maybe if you're interested in, I can explain later. And we have the full product lines. But the very nice things that we want to emphasize is that for the applications, we can work for different things. For example, we can work for direct compression. We can work for inhalation. And also we can work with viability and thermosensitive products. Also, it is very potential for encapsulation of API. And just to remind you with the two videos in the beginning, we also can achieve a very high flowability and hydration. So at the end, I would like to thank you for your attention. And also I would like to acknowledge the collaboration with our teams all over the world that you can see here, that most of the time the data is provided also by our colleagues in the US, in France, and also in Australia. So yeah, I finished my presentation today, and if you have any questions, just please feel free.
Thank you, Dr. Lay. That's an excellent presentation, interesting technology. I'm just trying to see how things were going with the Q&A, and there's a little bit of commentary from the organisers that people might not be able to type in there at the moment. So I think if there are questions out there, we've probably got time for one. Could I ask that whoever in the audience would like to ask a question, just to switch the mics on and speak?
There is.
Sorry.
There is a.
Yeah, got it. So thank you, Dana. I have a question written here from Karine Sagron, and she asks, for development scale, what is the minimum volume to use?
Yeah, so I would like to come back to the slide that where we show different scales or different models. In this slide, you can see that, I don't know if you want to ask about model 32 or model 50. So let me explain. The number here or the index here is actually the maximum evaporation capacity. So it means that with model 32, we have the maximum evaporation capacity of 32 kilograms per hour. So of course, it depends on, is the maximum value. It means that it depends a lot. So if you really want to use the very high temperature with the very high flow rate, then you may achieve the 32 kilograms per hour. But I guess that you don't want to use that very high temperature, and you want to dry something like which is more gentle, and then of course the capacity will be lower. But of course we will have to know like some more data, some more input parameters to answer this question.